Hello viewers. The planning and design of large caverns placed side by side require a detailed scientific analysis to base their designs on. Each such case in young Himalayas poses a complete different set of challenges and therefore cannot be designed merely on empirical basis. The lapses committed in the geological investigations, in the layout planning, and in the designs can be catastrophic in such cases. In this case study, I am going to present an insight on the mechanism that the rock mass was subjected to in the run up to the formation of a huge cavity of the size of a football field and of a height of one third the height of Eiffel Tower. The cavity happened through the Downstream Surge Gallery crown of the project Punatsangchhu-II hydroelectric project in Bhutan. The crown, having excavated and supported since 2013, the massive rock mass failure occurred after 3 years on 3rd March 2016. Unfortunately, 6 technicians got buried dead under the falling muck and billions of rupees got wasted, and an uncertainty with 6 years as of now got crept in to the completion of the project. In this case study, I'll be referring to international literatures and also I'll be referring to the findings of Norwegian Geotechnical Institute's study of this case, and also I'll be referring to the results of a 3D numerical analysis which was carried out by a renowned institute of India, National Institute of Rock Mechanics, to support my insight on the mechanism of the failure. Excavation of the powerhouse complex was started in 2012 with construction of main access tunnel to the powerhouse and construction added to the downstream surge gallery taken up in 2012. A shear zone met in the construction edit and the main access tunnel to the powerhouse in 2012. The resident geologist of the project apprehended that if the shear zone didn't get pinched, it will cut across the 3 caverns of powerhouse, transformer hall and downstream surge gallery. Accordingly, the same shear zone which was apprehended in 2012 did meet the 3 caverns in their central gullet in April 2013. A 3.5 meter thick major shear zone was encountered at RD 124 meter of the downstream surge gallery, which had inclination of 45 degree to 60 degree and an orientation of north 30 degree east, which was cutting all through above the crown to bottom of the downstream surge gallery. It resulted in formation of a hanging wall, and a 9 meter high chimney was got made in the downstream surge gallery's central gullet at RD 124 meter. This necessitated to change the layout and design of the 3 caverns in April 2013 when the revelation of major shear zone in downstream surge gallery's central gullet had happened. The designers, taking heed of the suggestion of the resident geologist of the project, did alter the layout of the powerhouse and transformer hall caverns by shifting the 2 caverns, that is of powerhouse and transformer hall, by 36 meter and 80 meter respectively to the southern end of these caverns, thereby to avoid their cutting by the major shear zone to a great extent. Excavation of the 3 caverns was started from their southern ends. The starting point of excavation at the southern end in the downstream surge gallery was accessed earlier than the starting point of excavation in the powerhouse and transformer hall. The excavation in central gullet in the downstream surge gallery was thus progressing ahead of the excavation in the powerhouse and transformer hall. The major shear zone was therefore met in the central gullet in the downstream surge gallery at RD 124 meter, while the excavation in the powerhouse and transformer hall had yet not progressed to those reaches where the shear zone would have been encountered in powerhouse and transformer hall, respectively. The resident geologist of the project suggested to the designers at that time that in order to avoid the cutting of the three caverns by the shear zone, their layout be altered and it be redesigned. Partially agreeing to this advice of the resident geologist, the designers had altered the layout but of only powerhouse and transformer hall by shifting these two caverns towards south by 36 meter and 18 meter respectively. However, the layout of the downstream surge gallery was left unaltered and was thus left to be intersected in the middle of the downstream surge gallery throughout its full depth of 58.5 meter by the shear zone. The hanging wall reach, which was following the shear zone in the downstream surge gallery, comprised of multiple set of joints, fractured rock mass, with joints filled with clay and crushed material. At that time, during April to December 2014, a crucial decision should have been taken by the designers for avoiding the downstream surge gallery to be cut by shear zone. As the function of the downstream surge gallery is only to provide enough volume which can supply efficiently water to the tail race tunnel on sudden shutdown of the turbines, and also can accommodate the discharge coming from the turbines immediately on sudden start of the turbines before it is gradually released in the tail race tunnel. This function can be achieved by providing an interconnected set of smaller chambers with equivalent volume of the one huge downstream surge gallery. The project management had at that time suggested to the designers that in order to avoid cutting of the downstream surge gallery by the shear zone, it can provide a distributed arrangement of smaller interconnected chambers instead of one huge cavern. However, the designers preferred to keep the huge size of the downstream surge gallery and did not alter the layout of the downstream surge gallery too. The criticality of these numerous joint sets and the major shear zone together, resulting in formation of potentially unstable wedges due to their dip, which was steeper than the angle of internal friction of the rock mass, is depicted in the stereonet shown here. The 8 types of sets of wedges formed out of the intersection of vertical and subvertical joint sets, which were actually present, was made out of intersection of joints J2 and J3, J3 and J7, J5 and J7, J2 and J5, J5 and J4, J3 and J8, that is shear, J3 and J4, and J3 and J6 are all very critical and potentially very unstable. These joint sets which form these wedges are vertical and subvertical and are much steeper than the angle of internal friction of the rock mass. With the presence of crushed material and clay in the gaps of these joint sets, they make a large zone of stress relieved rock mass. The hanging wall side of downstream surge gallery, situated between RD 136 meter to RD 195 meter in the north of shear zone, comprised of rock blocks assemblage with their joints filled with fractured and crushed material. Thus, the rock mass in hanging wall has a large variability of strength compared between the intact rock and the rock mass. The uniaxial compressive strength of the intact rock is 55 MPa. The uniaxial compressive strength of the 3.5 meter thick shear zone is 3 MPa. The uniaxial compressive strength of the rock mass in the hanging wall is only ranging between 1.08 to 2.84 MPa. The strength of rock mass is reduced to a value of 2 MPa, whereas its constituent intact rock is having strength of 55 MPa. That is due to the fact that the rock mass in hanging wall is excessively jointed with joints filled with fractured and crushed material, which makes the rock mass very weak. This slide shows the results of the numerical analysis done by the contracting agency and conveyed to the designers in 2014 December. It shows how, with the increase in the depth of the excavation, the massive yielding will take place in the rock pillars of the Downstream Surge Gallery. The left side diagram shows the extent of the yielding that would take place in the intervening rock pillar between the transformer hall and the Downstream Surge Gallery when the excavation depth would reach 2/3 the height of the Downstream Surge Gallery. That is to a depth of around 35 to 40 meters of excavation. And the right side diagram shows the extent of yielding that would be happening in that very intermittent intervening rock pillar between the transformer hall and the Downstream Surge Gallery when the excavation of the full depth of the Downstream Surge Gallery would have reached. As the excavations in Downstream Surge Gallery proceeded further in its benching, the shear zone was seen to be cutting the both walls of Downstream Surge Gallery, and the shear zone was traversing at steeply dip of 45 to 60 degree north, 30 degree east. In November 2014, benching had reached at elevation 608.5 meter. At that instance, subsidence of 55 mm occurred from RD 130 meter to 170 meter in downstream wall, and a subsidence of 20 mm was seen in upstream wall from RD 170 meter to 180 meter at elevation 618 meter. The design of rock support in the walls after the encounter of the subvertical shear zone in the walls was changed to an addition of concrete cladding on the shear zone intercept with 15-meter long rock bolts provided of 36 mm diameter to stitch the intercept portion of the walls. The excavation of 3 caverns of the powerhouse complex, having started in March 2013, had progressed as on 2nd March 2016 to different stages shown in the green colored shades in the slide. Each stage of the excavation was properly provided with the designed support measures adopting best engineering practices and standards. The powerhouse cavern had been excavated to its full depth of 52 meter with 6 pressure shafts excavated fully entering through its upstream wall, the 3 huge bus ducts, an emergency tunnel and a connecting tunnel, as well as 6 draft tubes had been fully excavated emerging out from the downstream wall of the powerhouse cavern, thus making the powerhouse cavern structurally most precarious with multiple openings existing in its both upstream and downstream walls. The transformer hall cavern 2 had been fully excavated to its full depth of 26.5 meter. Despite the vulnerability of the powerhouse cavern being more to any instability, it was rather the downstream surge gallery which, though had only been excavated through a depth of 35 to 40 meter out of its total depth yet to be reached of 58 meter height, met with a roof collapse on 2nd March 2016. This slide shows a typical correct design approach for large caverns in highly fractured rock mass. As was indicated earlier in 2014 in a numerical analysis done by civil contractor who was constructing the powerhouse complex in the project, that there will be widespread yielding in both walls of Downstream Surge Gallery as benching would progress. Therefore, the management had suggested the designers to either bifurcate the Downstream Surge Gallery into smaller chambers, which was not agreed to. Thereafter, the management suggested to provide wall beams at the SPL and cable anchors in the crown through this suggested wall beams and throughout the depth of Downstream Surge Gallery walls to strengthen and provide structural stability to the Downstream Surge Gallery. This was not adopted by designers, whereas it was quite known by that time that rock pillars are sheared and are behaving like a pre-cracked section. The 3D analysis done by NIRM in 2018 ratifies that the rock pillars in the hanging wall side stood widely yielded. The analysis shows that without the provision of wall beams and cable anchors in the insufficiently thick rock pillar intersected by the shear zone, dividing it into two pre-cracked blocks, the upstream rock pillar and the downstream wall of the Downstream Surge Gallery between RD 145 meter to RD 195 meter stood extensively yielded up to a depth of 15 meter into their thickness, with the strength to stress ratio of 0 in the yielded reaches. A paper was published in 2003 in the International Journal of Rock Mechanics and Mining Sciences, authored by C.D. Martina and others, titled Stress Instability and Design of Underground Excavations. The paper presented the causes of a raveling failure which happened in a mining stop. The stop was 35 meter wide, 45 meter long and had 180 meter height. The stop had good quality rock mass conditions, but at the same time it suffered from the following conditions. Firstly, there was a hanging wall present which dipped at a 65 degree to 85 degree. Secondly, the hanging wall rock mass consisted of Blocky Norites rock with one subvertical set at approximately 1 meter spacing and a second set of horizontal continuous joints also present at 1 meter spacing. These fracture sets resulting from the joint sets formed potential wedges in the hanging wall. The geological strength index of the rock ranged from 60 to 85 with compressive strength of 25 to 100 MPa and tensile strength of minus 0.4 to minus 2.65 MPa and a modulus of 27 to 80 GPa. The simple wedges thus formed in such a rock do not usually lead to progressive raveling. However, due to the geometry of the stop and because of presence of a precariously dipping hanging wall in which there were potential wedges made by multiple joint sets, therefore a zone of relaxation extended in several tens of meters into the hanging wall. The grey shaded portion seen here in the plot of stresses contours show the zone of relaxation formed in the hanging wall. A huge progressive raveling failure occurred in the hanging wall where the confining stresses had become less than zero, that is tensile. Let us review the principal stresses in the downstream surge gallery in its excavated state in a reach starting immediately after the shear zone towards the north in the hanging wall portion. The results of the 3D numerical analysis carried out in 2018 by NIRM shows that the value of major principal stresses which are aligned parallel to the longitudinal axis of downstream surge gallery in this reach of hanging wall were marginalized to a value of 2 MPa after excavation had reached to a depth of 35 to 40 meter in downstream surge gallery as compared to the value of the in situ major principal stresses of 4.02 MPa that were before excavation present in this reach. The major principal stresses in the downstream surge gallery in the hanging wall portion thus has its value just equal to the uniaxial compressive strength of the rock mass. The relaxation zone above the crown of downstream surge gallery is seen extended to a height of around 100 meter above the crown. The fact that the major principal stresses are developed to a value of 7 MPa in the near vicinity of the crown in its limited thickness proves that the arch action stood very much developed in the crown in the hanging wall portion of the DSG also, which is pre-stressed by rock bolts. The most important prerequisite for the raveling failure to occur is that of the confining stresses becoming tensile. In the case of downstream surge gallery, the confining pressure was to be provided by the minor principal stresses as these were acting in transverse direction of the cavern. The 3D analysis done by NIRM establishes that the minor principal stresses present around and immediately above the crown in downstream surge gallery cavern in the hanging wall reach had become tensile. This slide shows the three-dimensional view of the downstream surge gallery and the other two adjacent caverns, that of transformer hall and powerhouse, showing that how it was only in the downstream surge gallery, which was cut so precariously by the major shear zone, which was dipping subvertically at an angle of 45 degree to 60 degree, dipping towards north and 30 degree direction. It was the hanging wall reach located towards the north of the shear zone where the confining minor principal stresses had become tensile and the other confining stresses, that is major principal stresses, aligned along the direction of the axis of the downstream surge gallery, had been reduced to merely 2 megapascal in a stress relieved zone which existed up to a height of 100 meter rising above the crown. The rock mass in the hanging wall comprised highly jointed and fractured rock mass. We may note that a moderately high confining stresses are required to keep the jointed and fractured rock mass together, else it will behave as merely an assemblage of rock pieces which are loosely packed and are prone to fall under gravity forces in unconfined conditions. In such a situation, the geometry of the hanging wall and geometry of the inclined discontinuities would guide the gravity induced and structurally controlled fall of the rock blocks lying in the hanging wall. Thus, we see that similar to the conditions present in the case of mining stop discussed earlier, where raveling failure had happened exactly along the profile of a region of loss of confinement arising in the hanging wall, which was made of blocky rock mass. Here also, all the prerequisites which could result in raveling failure were present together only in Downstream Surge Gallery. Firstly, the rock mass in Downstream Surge Gallery was Blocky II, comprising of numerous joint sets. Second, these fracture sets formed potential wedges cut along the precariously inclined discontinuities made by numerous subvertical joint sets combined with near horizontal foliation joint sets. The steeply dipping major shear zone, which cut the downstream surge gallery all through its depth, right from above the ground till bottom of the downstream surge gallery, precariously placed the wedges of blocky rock mass which were prone to fall under their own weight. Fourthly, the zone of relaxation in the hanging wall ridge was extending to about 100-meter height above the crown, just like in the case of the 180-meter height of region of no confinement in the mining stock discussed earlier. Next, the confining stresses in the crown in the hanging wall ridge are reduced to less than zero in the case of downstream surge gallery also. The rock blocks subjected to tensile forces had thus become a disintegrated mass, making a big threat of loss of arch action in the crown. The geometry of inclined discontinuities forming the potential wedges would guide the gravity induced and structurally controlled fall of rock blocks of the wedges in the hanging wall. So, a stage was all set for a progressive raveling of the disintegrated rock mass present in the hanging wall reach of the downstream surge gallery to be triggered any moment with instabilities increasing with increasing depth of excavation in downstream surge gallery. This slide shows the sectional plan of the downstream surge gallery at SPL level, which establishes that in the widespread stretch in the hanging wall to the north side of the downstream surge gallery, the minor principal stresses are reduced to sub-zero, that is tensile in nature. As discussed in the earlier slides, that due to presence of the steep shear zone and the multiple sets of joints which were filled with crushed material, the rock mass lying in the hanging wall side in the rock pillars in the downstream surge gallery stood widely yielded. These widely yielded rock pillars were supporting the crown in the downstream surge gallery. This distressed rock mass in the yielded rock pillars was undergoing increased displacements with the increase in depth of excavation in the downstream surge gallery. The paper of the case of raveling failure in the mining stops, authored by C.D. Martina and others, discussed in earlier slides, states that with increased rate of displacements strain, the rock mass behave more and more brittle. Therefore, as the displacements as SPL level in the walls of Downstream Surge Gallery increased with the increase in depth of the excavation, the increased displacements loosened the keystones at the SPL in the Downstream Surge Gallery. The displacements at the SPL level in both the walls of Downstream Surge Gallery had attained a value of 100 millimeter, which caused rock blocks at the bearing level of the crown getting dislodged and thus making the crown fail in its bearing. With the increased displacements of the loosened keystones at the SPL in the Downstream Surge Gallery walls, the keystones at the SPL level in the rock pillars got dislodged. Consequent to dislodging of the keystones in the walls at its bearing level, the arch action in the crown could not be sustained, as the crown comprised of rock pieces which were lying unconfined due to the confining stresses having become tensile, and the other major principal stresses responsible for confining the rock pieces also got marginalized. These disintegrated rock blocks were let in unconfined state consequent to the withdrawal of the support from the dislodged keystones in the rock pillars of the Downstream Surge Gallery. These rock blocks fell loose under their own weight. The major principal stresses in a zone stretching in a height of 100 meter or so above the crown in the ridge following the traverse of the shear zone in the hanging wall too had been reduced to meager value of 2 megapascals. This distressed zone rising above the crown was only present in the case of Downstream Surge Gallery, which made Downstream Surge Gallery different from the case of distress in powerhouse and transformer hall caverns. The phenomenon of disintegration of rock blocks progressed towards the higher elevations in this distressed zone above the crown in the Downstream Surge Gallery. The raveling fall of these loose rock blocks lying in the distressed zone happened in suddenness because the rock mass, with the increase in the rate of strain, behaved more and more brittle. It is thus established that numerous potential wedges, due to absence of confining pressure, had resulted in the fractured rock mass to undergo gravity-induced and structurally controlled fall of rock blocks in the hanging wall of Downstream Surge Gallery. The geometry of the inclined discontinuities further guided the gravity-induced and structurally controlled fall of the blocks. It is significant to note that the shape and size of the cavity formed from the rockfall is identical to the shape of zone of relaxation seen in the plot of major principal stresses in the reach of the hanging wall, but was so seen only in the Downstream Surge Gallery and not seen so in powerhouse and transformer cavern with minor principal stresses becoming tensile in the affected reach. Let me summarize the phenomenon happened in the Downstream Surge Gallery which led to the huge failure in the crown. Going through the prerequisites for a raveling failure of rock mass to happen, the only condition which was exclusively only fulfilled in the Downstream Surge Gallery and was not present in the powerhouse and transformer hall caverns was that of cutting of the Downstream Surge Gallery in its middle reach right from much above the crown to the elevations down till the bottom of the cavern. Thus the condition involving presence of hanging wall phenomenon in a rock mass comprising multiple joint sets which gave rise to formation of multiple sets of potentially unstable wedges was only present in the case of Downstream Surge Gallery alone. Therefore, it was the Downstream Surge Gallery alone which bore the brunt of the effect from presence of the hanging wall, that both the massive yielding in the walls and loss of confinement pressures happened in both directions of minor principal stresses and major principal stresses in the Downstream Surge Gallery in the hanging wall reach alone. Whereas in the powerhouse and transformer hall caverns, the major principal stresses remained intact to confine the rock blocks in the crown. There was no much yielding in the wall supports in powerhouse and transformer hall cavern, since the shear zone did not intersect the powerhouse and transformer hall caverns as precariously as it did the Downstream Surge Gallery, and it merely touched the gable ends in transformer hall cavern and even much less in powerhouse cavern. Despite the depth of excavation reached in powerhouse cavern being much more and the multiple openings of the pressure shaft and draft tubes and 5 tunnels for bus ducts etc., making the powerhouse cavern walls more vulnerable to instability, but it was the Downstream Surge Gallery where the shear zone was cutting both the walls and the crown of the Downstream Surge Gallery precariously, which proved the Downstream Surge Gallery becoming unstable. As a result, besides the confining pressure which was to be provided to ensure stable arch action in the crown being reduced to tensile stresses in the caverns, a big difference seen in the case of Downstream Surge Gallery is the presence of a huge zone of relaxation developed in the crown, but that happened only in Downstream Surge Gallery, in a reach lying over the traverse of the shear zone in the hanging wall reach, wherein even major principal stresses were reduced and marginalized. The shape and size of this relaxed zone is remarkably similar to the size and shape of the raveling cavity formed in the Downstream Surge Gallery crown. Thus, as was informed earlier in 2014 by the contractor of the powerhouse complex that the walls in the Downstream Surge Gallery would be yielded in the hanging wall reach, and this fact is also ratified in the three-dimensional numerical analysis done by Niram in 2018. This huge distress zone of the yielded rock mass was all set for a raveling failure to happen when an instability is triggered. The dislodging of the key rock blocks from the walls at the SPL supporting the crown in the Downstream Surge Gallery provided the much awaited trigger for setting in the action of instability in the arch and eventually for the fall of the crown of the downstream surge gallery, in which loose rock blocks were already subjected to tensile forces. This fall of rock blocks from the immediate vicinity in the crown was followed by a raveling fall of loosely packed rock blocks under their own weight, which formed the huge cavity in a short duration